Okay, I wanted to do a little bit of video support for hypothesis testing because I feel like there's still a lot of struggle in terms of the process. I've got the sheet over here with the steps, and I'm just going to do a problem and go through it. So the beginning is always kind of establishing H naught and HA. So let me get started there. And um, I it's not clear from the formation of this what the reason I'm investigating the claim. I guess I would just add in here to give myself a better shot of writing. I mean, I got a good idea of what H naught should be. Um, and I guess let me just start there and then I'll kind of add in a few more words here. But this is the basic starting point, right? That the average American or Americans watch television on average 4 hours per day. So this is going to be my watch time is equal to 4. Now, if depending on the way that the kind of disbelief is framed, I might be saying not equal to 4. I might be saying I think it's less than 4. So I'm going to say Ben thinks this number is too high because people don't watch as much TV as they used to. He decided to go. Okay. So then what I'm essentially saying is I think the number is less than 4. So I would probably change this to be equal to or greater than 4 with the alternate hypothesis of the amount of television that people watch is less than 4. I'll just make W clear up here. W is the average number of hours that Americans watch TV per day. Okay. So again, this is a part where people are kind of struggling. Focus on the fact that there is some number that's stated as an average. We want the equality to be in the H naught, and then from there, there's some kind of figuring out of the less than, greater than, not equal to, whatever. And there's some implications for that, but in general, this is the really significant part, that the equal sign and the number need to be in the null hypothesis, because that's how we're framing our investigation. So from there, I'm ready to proceed on to the next step. So let's take a look here. Set acceptable level of strangeness. So I'm going to pick significance level of 1%. I'm going to set a pretty high bar here in terms of what I'm looking for. So 1% is my significance level. And I've got a standard deviation of 2 for the population. We don't know how we know that, but again, a big part of what the kind of test we're doing, we need that particular formula. So I went out and did the research, 135 responses, 2.3 hours is my average from my sample. And now I'm going to apply that formula. Let me go pull that up here from this one. Here we go. So I'm just going to copy this and bring it back over. Okay, so what do I need here? I need to know my average, 2.3, minus the presumed average, which is 4. And then I'm going to divide that by the standard deviation, which is 2, but I'm going to divide that by the square root of 135. So these are the two parts. This is the top. This is the bottom. I can put it all together into one piece. I just need to be careful to do it with parentheses. So doing it with parentheses all in one step would be 2.3 minus 4 divided by new parentheses 2 divided by the square root of 135. I'm not putting the equal sign just so it doesn't disappear. So now I'm going to put this in. First of all, let me start by saying I expect the answer to be negative because my survey result was below the mean, which is good because that was my alternate hypothesis. I think that it should be lower. But let's see if it's strange enough. That's essentially what we're doing when we do a hypothesis test, is we're seeing, is the result strange enough? We know that, if I go out and I sample Americans, I'm going to find something that's probably not exactly the same as the 4 hours, which is the supposed average. Even if that is the average, if I go out and sample people, I'm going to get something that should be close to the truth. Now, how close to the truth is kind of a randomness aspect to it, and that's where this the whole idea of the central limit theorem comes in, because I'm looking at, oh, I forgot the closing parenthesis here. I'm looking at the sampling distribution, which is the idea that if I go out and I randomly sample Americans over and over and over again, I'll get a normal distribution where the average mean is at 4, whatever the real average is. And then it has a standard deviation, which is determined by my sample size. So the larger the sample size, the smaller the standard deviation. And so what's happened here is I've gotten a really low z-score. This is called my z-test. And I'm ready to conclude kind of right now, but I'll kind of walk through the steps, and then I'll redo this so that it gets sort of more interesting. So this number, this is kind of the first step, right? I've gotten the let's go back here. I've gotten my null hypothesis, the alternative hypothesis. I've set the level of strangeness. I collected the data. Now I'm into the test statistic of figuring out how many z-scores away is my sample mean from the supposed mean. And the answer is negative 9.87. Now, negative 9.87 is a lot of z-scores below the mean. Remember, what this means is this value is 9.9 standard deviations below the mean. And keep in mind that the empirical rule says 99.7% of our samples should be within 3 standard deviations of the mean. Well, I'm almost 10 standard deviations away from the mean. This z-score is a very, very strange value. Very rare, very improbable. And so what I'm going to do here is I'm going to conclude that my starting assumption must be wrong, because otherwise this result is so unlikely as to defy belief. So that's essentially what's happening here. And I tried to show kind of a mathematical example. I'll just do it here. The principle that we're operating on is, let's say we have an equation, and I don't know, we don't know how to solve the equation. I'll take something simple like x times 2 to the x equals x squared plus 9. This equation is actually very difficult to solve. So because I don't know how to solve it, I'm just going to say, let's assume x equals 2 and see if we got the right answer. I can plug it in and I can evaluate it. 2 times 2 to the 2 equals, there's a lot of 2's flying around here, 2 squared plus 9. Okay, so I can do some of that. 2 times 2 squared is 2 times 4, that's 8. 8 equals 2 to the second power is 4. 4 plus 9 is 13. I have arrived at something which is not true, or in other words, a contradiction. So I started with an assumption, it led to a contradiction, and what does that lead me to conclude? It leads me to conclude that, in fact, this assumption was wrong. And it's a way of approaching a problem and thinking through something logically. So in the case of the null hypothesis in this problem, we started with the assumption that the average number of hours that Americans watch TV per day is 4. And so we built our sample space around 4. We know that when we sample repeatedly, we're going to get a normal distribution centered around the same mean. And then once I set up my standard deviation, I can see, well, okay, I sampled and I got this result. Is it possible with the 2.3 down here? Is it possible that this is just, a random sample that's a little bit lower than the mean? Or does it cause me to reject my original assumption? And it should cause you to reject this. And again, that's based on the z-score. The z-score is the number that gets in there and helps us decide that. Okay, let's do one where I'm going to do the same question, but I'm going to do it in such a way that it's actually close enough that it's kind of interesting. Let's say I only did 35 responses, and this time I got 2.9 hours, and I want to know if this is crazy, and therefore I reject the null hypothesis. So I'm going back through here. I can stick with my significance level, although I don't know how close it is, so we'll just see what happens. And again, where I'm going to go next is I'm going to do my z-test. And to do that, I need 4 values. So I've got my average of 2.9. That was from my sample. I'm taking away 4. It's still going to end up negative. This time, my standard deviation is still 2, but my sample size is smaller. It's only 35 people. And I'm going to go ahead and do the division. This time, I'm not going to write out the parts to leave it there. I'll just do it all. Don't forget the division on the bottom. Square root of 35. Okay. Minus 3.25. We got a fighting shot here of getting onto the z-score table. I'm going to go ahead and use norm.dist. So remember, this is my z-score essentially. It's still pretty far down, negative 3.25. So we'll see equals norm.s.dist. And then I take my z-score. I say true. And I got a really small percentage, but at least I'm on the charts here. As a percent, I'm looking at 0%, 0.06%. So again, the fact that this is so low of a probability, right? This is the probability of this happening randomly. The fact that it's so low causes me, again, to reject the assumption that I started with, which is that the answer to the average is actually 4. I would be not surprised if 2.9 was my sample if that number were lower, right? So if I had started, say, with, let's say 3.5 hours per day. So then what changes is the distance from the mean is not so great. And then this number becomes less strange. And now we're sitting at a 3.8% chance of that happening. So now, even though in this context, if I did my research and there was a result that was lower than the mean that was supposedly there, it's not so low that at the 1% level, I would reject it because 3.8% is not below the significance level that I'm looking for. If I had picked the 5% significance level, then I would still reject the claim because, and I feel like I should kind of organize all of this so that we can see the difference in how things are panning out. So let's build a little table here. So we had the assumed average. The first time I did it, it was 4 hours. the sample size, the sample mean, the significance level. What else did I need? We haven't messed around with the standard deviation, but I guess let me move this one out because these four numbers, this is for the population. And again, this is where it's kind of fakey because how would I know the actual standard deviation for the entire population? So the first time I did this, the assumed average was 4. The sample size was 135. The sample mean was 2.3, and the standard deviation was 2 with a significance level of 1%. We did the math here. We took the sample mean, oops, I better use parentheses, sample mean minus the assumed average. I'm going to break it into parts actually. So this is the distance from the mean, from the assumed mean. Kind of do this and then do that and wrap text. Okay, then the standard deviation of the sampling space, which is equal to the standard deviation, but divided by the square root of the population, the sample size. Okay. And I'm going to go ahead and get rid of a few decimals there. And so then number of z-scores, or sorry, the z-test, which is the number of standard deviations in the sampling space away from the mean. It's a pretty complicated number here. Number of standard deviations in the sampling space that the sample mean is away from the assumed mean. And so this number is just the ratio of the distance divided by the standard deviation of the sampling space. That's where we got that negative 9.78 number. It was a pretty big number. Yeah, I don't need that many decimals. The next time, version 1. Version 2, I was like, okay, well, let's change the assumed average down to 3.5. I think I did it at 4 with the sample size of 35, the sample mean of 2.9. The significance level stayed at 1%. And so then I can apply these three numbers all at once. Minus 3.3, right, because that was the minus 3.25. So the conclusion here, let me just add this column in. Before I do that, probability of getting less than this sample mean. So I can change that norm.s.dist. This number true. Okay. And I can format these as percentages. I'm going to give a decimal just to show this is so small. You saw the number in scientific notation was like times 10 to the negative 21st. I mean, it's an incredibly tiny number. This is also very small, but it's actually starting to register. It's still below my significance level, so I reject the null hypothesis. And I would do the same thing here. Okay, the next time I said, wait a minute, what if I changed it to 3.5 with a sample size of 35, 2.9, standard deviation of 2, significance level staying at 1%. And now let's run it out and see what happens. Aha. So now with the 3.8%, I'm actually above the significance level. So it's rare, but not rare enough for me to reject it. So I don't have evidence to reject. I don't reject the null hypothesis. I can still say, boy, I feel like I'm still right that the amount of TV that people watch is less than 3.5, which was what the survey stated was the assumed value, but I don't have the evidence to reject it. And so maybe the answer is more study needs to be done with a bigger sample size, whatever. So I just want to point out that if I had those same numbers, but I changed my significance level to 5%, then the way that this changes, nothing changes in the calculations, but what changes is I'm back to rejecting the null hypothesis because the 3.8% is less than the significance level, and therefore I feel confident that I can reject it. Now, just to further blow your mind, if I had split this into two tails, done everything exactly the same, I'm going to add in another column here, one tail or two tail. Remember, two tail just means that this is not a percentage, this is a number. Great. 1, 1, 1, 1, 2. It just determines whether or not I need to split the significance level among two sections or not. So if this was a two-tail experiment, then I would be splitting my 5% between the two ends. Then that means there's really only a 2.5% threshold here for my significance level on the right side and also on the left side. So back to, and this would be in the case where I said, I don't know if it's greater or less than the average that's assumed. I just don't think that answer is right. So I'm going to do a two-tailed test. So then the significance level gets split. And if it gets split, notice what happens here in my final conclusion is that I would not and I probably would want a final each side's significance. So in a one tail, I'm leaving it the way it is because I'm dividing by 1, but in a two tail, I'm splitting it in half, which means the 2.5% becomes the significance on the left and the right. And now the 3.8% is above that, so I don't reject the null hypothesis. Boy, it's complicated. But the good news is that the math calculation part of it is just the ratio of these two things, the distance from the assumed mean, from the sample mean, and then this converted standard deviation of the population to the standard deviation of the sampling space. And in thinking about whether or not the null hypothesis is rejected, you really need to get the z-score into a single percentage or a probability so that you can compare it to the significance level. And the significance level, unless it's two-tailed, is exactly what it's stated. If it's two-tailed, you just cut it in half. And then it's a simple, is it less than that or is it not? If it's less than that, then we met the significance criteria and we reject the null hypothesis. If it's not less than the significance level, then we don't have enough evidence and we have to move on with our lives or go back and study it some more. Just out of curiosity, if I had gone back and done this one more time as a two-tail experiment, but I had said, God dang it, I was real close here, and I'm going to redo this. So I'm going to copy all of this, but this time I go back and I go back to my survey sample and I get more. And turns out that The sample mean this time was 3.0. Is it enough information to reject it? Let's find out. So first of all, the difference is negative 0.5. That's because I'm sitting at 3. The assumed average is 3.5. The standard deviation of the sampling space is going to be back down to this kind of smaller level because I have a larger sample size, which means that I can be more confident of the region where the sample should end up around. That's the value of sampling more. And now I can throw in my z-test, and now I can look at my percentage, and I'm back to reject the null hypothesis. So interestingly, even though in this study, we got the result of 3, which is not as far away as the 2.9, because of the larger sample, we actually end up being able to reject the null hypothesis because we have a stronger sampling space that's got a tighter center, and therefore getting a 3 was weirder than getting a 2.9 in this situation. All right. I know it's a lot. See what you can do to wrap your head around it, and don't be afraid to ask for help.